In this video, we're going to talk about Thevenin's theorem and Norton's theorem. And they're really similar to each other. Once you understand one, you know what the other one. And so what Thevenin said, you can take any circuit. You could have a circuit that looks like this. I'm just making some example, like 10-volt source with 10 ohm here, 7 ohm, 5 ohms, 4 ohms, and let's say this is my load resistor. What Thevenin said is we can take this circuit right here and replace it with an equivalent Thevenin circuit using Thevenin's theorem. So what does that equivalent circuit looks like? We're going to take all of this and replace it with a voltage source called Thevenin in series with the resistor called Thevenin. And there is our load resistor. And the question becomes, how do you find Thevenin and Thevenin? Well, Thevenin can be found by finding the V open circuit. We'll use that example in a few minutes. And Thevenin is equal to the R equivalent. If you are looking backward from this end, if you cut it right there and looking backward in that direction, what is R equivalent? So I'll say looking backward. So let's take this example and find what Thevenin and Thevenin is. Again, the numbers might be really ugly because I didn't even think about any of these numbers, just throw them up there. So here's my circuit. I'm chopping it right there. 10 volts, 10 ohms, 7 ohm, 5 ohm, 4 ohms, and this is my V open circuit right there. If we cut the circuit open right here, we measure the voltage between this end and that end. What are you going to read? Since that's open, that means the current going this way is actually 0, because it's an open circuit right there. If the current is 0, if you remember from circuits, the voltage is V equals I times R. So if I is 0, what's 0 times 4? 0. What's 0 times 5? 0. So the voltage drop here is 0, which means these two resistors are gone. There is no voltage drop across them. So I can take them out. If I'm looking for the voltage right there, plus on the top, minus on the bottom, I can take these two resistors out because there'll be no drop across them. And now the voltage V open circuit becomes the voltage across the 7 ohm. So what is that voltage equal to? It's voltage division. 10 times 7 over 7 plus 10. That's 70 over 17. Divided by 17, which is 4.12. That's V open circuit, or Thevenin. So Thevenin now, which equals V open circuit, that's going to equal 4.12 volts. Next step is to find Thevenin. How do we find R Thevenin? So here's V Thevenin. Let's look at R Thevenin. And to find R Thevenin, we need to find R equivalent. But wait a minute, we have sources here. So what do we do with these sources? Well, if you have a voltage source, when you're looking for R Thevenin, if you have a voltage source, you need to replace it with a short circuit, just a wire. And if you have a current source, we need to replace it with an open circuit. Again, you only want to do that if you don't have dependent source. If you have a dependent source, we got a different story here. The problems you're going to be seeing in this actually class, I don't know if you're going to see dependent sources there. But if you do encounter that, then to find R Thevenin, what you need to do is find I short circuit, put a wire there, find I short circuit, and R Thevenin will be V open circuit over I short circuit. But if you only have independent sources, so I should say R Thevenin only independent sources. For dependent sources, I'll put it there, I wasn't planning on to. For independent and dependent, and dependent sources, R Thevenin is equal to V open circuit over I short circuit. And maybe I'll do an example on each one of these. So let me finish that example first. I'll come back and add actually a dependent source to a problem and go from there. So let me find R Thevenin for this circuit. So let's find R Thevenin. Let's kill the source or eliminate the source. The word kill is not nice. Eliminate the source. So that's a voltage source. We're going to make it a short circuit. So looking back, what is the R equivalent? Quickly, I know these two are connected in parallel. And believe it or not, these two are connected in parallel. So the equivalent of these two, the 10 and the 7, will be the product over the sum. 10 times 7 over 10 plus 7. And the equivalent of these two, the product over the sum, 4 times 5 over 4 plus 5. It's always the product over the sum for two resistors. So this will be 10 times 7, 70 divided by 17. This is 4.12 ohm. And that one will be 4 times 5 is 20 divided by 9. This is 2.22 ohm. So now you can take that circuit and replace the two resistors on the top with one of 2.22 ohm. Replace these two with one that's 4.12 ohm. And these two are connected in series, so R equivalent, which is R Thevenin, is going to equal 2.22 plus 4.12, which is 6.34 ohm. So my equivalent Thevenin now, my Thevenin equivalent circuit should be V Thevenin, R Thevenin, and this is my resistor that was at the end that I cut out, which is R sub L. Let me put it there. And V Thevenin is equal to what? 4.12. I think we got that early. And R Thevenin is equal to what? 6.34. So if you take this circuit here and you attach R sub L to it, you get the same result as this circuit with R sub L attached at the end. This one is the equivalent of this one. Let's put them like this. This one here is the equivalent of this. Now let's put a dependent source. I wasn't planning on doing it, but since I opened my mouth, I'll show you what will happen if you have a dependent source. Again, let me make a circuit, make it up here. I like to use a black color for that. Five volts. 6 ohm. I can do a dependent voltage or current, doesn't really matter. I'll put a dependent current just to be different. And the value of that, 5 times I sub x. This is, I'm going to define this as I sub x, the current through that resistor. And let's give this resistor some value. That's 4 ohms. And this is my load resistor, R sub L. I can give it any number. I can make it adjustable too. So what I'm going to do is cut the circuit right here and Thevenize this circuit. Find the equivalent Thevenin of this circuit. The one in the red dotted box. So my job now to take this one, this whole circuit, and replace it with an equivalent one. Is going to have a value of voltage here called V Thevenin. And it's going to have a resistor in series with it called R Thevenin. And this is my R sub L. So once I know R Thevenin and V Thevenin, these two circuits will be equal to each other. Again, let's start by finding V Thevenin. V Thevenin is actually V open circuit. So let me take my circuit here. 5, 6, 5 I sub x, 4 ohms, I sub x, and this is my V open circuit right there. So it's really, by looking at it, it's the voltage across that 4 ohm resistor, which equal to what? 4 times I sub x. So if I know what my I sub x is, I'm done. How do you find I sub x? Well, I can use what? Kirchhoff voltage law. I can assign a current in this direction, we'll call it I sub 1, and I'll assign one in this direction, that's the same as I sub x. So let's now write an equation. Kirchhoff voltage law says sum of the voltages in a closed loop is 0. I can't use this loop. I can't use that loop. The reason? I don't know the voltage across this source. Unknown to me. So I have to travel this way. And let's say I'm going to go in this direction, clockwise. So I'm starting with the negative source. I can make that a negative 5. Plus, because I'm entering this, going to be a plus, 6 times I sub 1. Plus 4 times I sub x, that's equal to 0. That's my first equation, or 5 equals 6i sub 1 plus 4i sub x. Well, I have two unknowns in that equation. That's not going to help me. I need a second equation. As I said, I can't do an equation here, and I can't do one here. So what should I do then? I can use this dependent source. The current pointing upward, 5i sub x, should equal, notice, this I sub x is pushing upward, so it's I sub x minus I sub 1. And if I move the I sub x to this side, 4i sub x equals negative I sub 1, or I sub 1 equals negative 4i sub x. That's my second equation. Now do that substitution to this one. 6 times negative 4i sub x plus 4i sub x is equal to 5. Negative 24i sub x plus 4i sub x equals to 5. Negative 20i sub x equals 5. I sub x equals negative 5 over 20, negative 1/4 or 0.25 amps. So now I know what my V open circuit. I said V open circuit is right here, 4 times I sub x. So 4 times, what's I sub x? Negative 0.25. And that's negative 1 volt. Next, I need to find I short circuit now. If I need to find R Thevenin, I need the short circuit current. So let's find R Thevenin. R Thevenin equals V open circuit over I short circuit. So I need to know what I short circuit. What is I short circuit here? So let's take this circuit and put a wire here. 5 I sub x this is 4, I sub x is here, and this is my short circuit. Now we're putting a wire here. And what is the current coming down here? So what do you notice about that? First thing I notice is this one in parallel with this. That means since this is a short circuit, assume it's an ideal wire, there is no current going to go through this. This is gone. This is 4 ohm in parallel with 0. The product over the sum, 4 times 0 is 0 divided by the sum of them, which is 4. So this resistor is gone, and the current through that is 0. So here's my circuit now. 5, 6, 5 I sub x, the other thing I know that I sub x is 0. If I sub x is 0, that means 5 times I sub x is 0. Now let's look at this circuit. If this is your ground here, that means this voltage is 0. This is a wire connected that's 0 voltage. There's a current going this way. Ohm's law says current is the voltage, which is 5 minus 0, which is 5 divided by 6. Voltage over the resistor. The voltage across that resistor is the difference between this end and that end. This is 5 volts here, that's 0 volts. So the difference is 5 minus 0 divided by that resistor, which is 6. There's a current of 0 going in this way. And KCL, Kirchhoff current law, says if you take all the current entering a node, that's a node here, should equal all the current leaving that node. We have 5 over 6 going in. We have 0 going in. And what's leaving that node? I short circuit. So what is I short circuit equal to? 5 over 6. So what's my R Thevenin equal to? It's V open circuit over I short circuit, which is negative 1 over 5 over 6, which is negative 6 over 5. Negative resistor might be confusing to some people. You got to be patient with that. Hopefully, if you take other circuits classes, you'll understand what that is. And now you have the equivalent Thevenin. Let's see what Norton. If you understood Thevenin now, Norton is really simple. It's just little minor changes. Norton says you can take your circuit, your linear circuit right here, whatever circuit you have, and this is your R sub L. I don't want to draw a circuit even there. You can replace that according to Norton here. This is Norton theorem. You can take this circuit and replace it with a current source with the value of I Norton in parallel with R Norton. And that's your R sub L. And the question is, how do you find I Norton? How do you find R Norton? I Norton is the I short circuit. Remember this example we just finished. We had to find I short circuit. If I was doing Norton equivalent, My I short circuit, that's I Norton, 5/6. You put a wire here and you calculate what the current going through that wire. That's your actually I Norton. What's R Norton then? How do you find R Norton? That's the same as R Thevenin. So what does that mean? That means if you have only independent sources, so you want to replace the voltage source with a short circuit, the current source with an open circuit, and find the equivalent, R equivalent. If you have an independent and dependent sources, then R Norton will be V open circuit over I short circuit. The same way we did Thevenin, we'll use those techniques to find R Norton. So there's really a relationship between Norton and Thevenin. It's actually source transformation for those people who cover that topic. So I'll show you the relationship. If you have a Thevenin circuit like this of V Thevenin with R Thevenin here, you can change that to a Norton equivalent. We can take this and change it to Norton equivalent. Norton equivalent says you're going to have a current source of I Norton in parallel with R Norton. The question is, how do you find I Norton if you know V Thevenin, R Thevenin, and how do you find R Norton if you know these guys? So we'll start with the easy one. R Norton will be the same as R Thevenin, so you don't have to do anything to that. And I Norton, using Ohm's law, it's voltage divided by the resistor, so it's V Thevenin divided by R Thevenin. Here's a quick example. If I have a Thevenin equivalent of 20 volts here, in series with 4 ohms, I can replace that with the current source in parallel with the resistor. The value of that resistor doesn't change, the same as this. But the value of the current source is going to be 20 divided by 4, which is what? So I Norton here is going to be 20 divided by 4, which is 5 amps. I'm going to replace this one with 5 amp source in parallel with 4 ohm resistor. The reverse now. If you have a Norton equivalent, I Norton, in parallel with R Norton, I can replace that with, or change it to Thevenin equivalent. That's V Thevenin in series with R Thevenin. And what's R Thevenin is going to equal to? Is going to equal to R Norton. What's V Thevenin is going to equal to? Ohm's law, V equals I times R. I Norton times R Norton. So here's an example. A 3 amp source here in parallel with a 10 ohm resistor. I can change that to a voltage source in series with a resistor. The resistors don't change, that's still 10. V Thevenin now, Ohm's law is going to say I Norton, which is 3, times the resistor, which is 10, and that's 30 volts. So if you take a voltage source of 30 volts in series with 10, That's equivalent to a current source of 3 amp in parallel with the 10. And that's the relationship between Thevenin and Norton.